Welcome to the 2023 Robert M. Walker Distinguished Colloquium series. Today, the colloquium. Tomorrow evening, 7 p.m., the public lecture. I'm pleased to welcome all of you. It's good to see so many of you here, faculty, students, friends of the Max Center, researchers. It's great to see you all here today, and it's my pleasure to introduce our distinguished speaker, Professor Meenakshi Wadhwa from Arizona State University, where she is the director of the School of Earth and Space Exploration, also known as CC.
Yep.
And she has a great many responsibilities there as well as elsewhere. Well, let me just tell you a little bit about her. She received her doctorate from, wait for it, some of you remember this, Washington University in St. Louis in just a few years back.
Don't
Exactly when. Say when.
You don't say.
After receiving her PhD here, she did a postdoc at Scripps working with Gunther Luckmar, right? And then she went on to Chicago to work at the Field Museum as the curator of meteorites there. And after a few years there, she went to Arizona State University as a professor and worked her way up through the ranks. She served as the curator of the fabulous meteorite museum at Arizona State University. And then in 2019, you became director of the School of Earth and Space Exploration. And I think they gave you a break and put somebody else in charge of the meteorites.
Yes.
Yeah.
Actually, Rhonda Stroud, who was an alum of
That's
WashU.
right. Rhonda is there now. That's fantastic. She has done a lot of things. She's been to Antarctica twice to collect meteorites. Her expertise is in the analysis of solar system materials, and she holds with her previous postdoc, Audrey Bouvier, the record for the oldest object in the solar system dated, right? Still, yes, fantastic, and continues excellent work in her laboratory. She has also worked with some planetary science missions, notably Genesis and the Mars Science Laboratory, MSL, and partly as a result of her work with MSL, but also going back to the time she was a graduate student working on Martian meteorites. She has been selected to be the chief scientist or the lead scientist, principal scientist at the Jet Propulsion Lab for Mars sample return, and I think we'll hear a little bit about that. And so she currently holds a distinguished visiting scientist position at JPL. She has, in addition to these things, served as president of the Meteoritical Society and chaired the science committee of the NASA Advisory Council. Pretty lofty thing to do. She has received many, many awards, and I have to use my cheat sheet for this. She's a recipient of a Fulbright Academic and Professional Excellence Award, 2015, Guggenheim Fellowship, 2005, the Near Prize of the Meteoritical Society. She's a fellow of the Meteoritical Society, the Geochemical Society, the American Geophysical Union, the European Association of Geochemistry, the Explorers Club, and probably some other things that I have not listed here. She was awarded the J. Lawrence Smith Medal of the National Academy of Sciences, a very high honor for someone who explores and studies meteorites. And she was just this past year elected to the National Academy of Sciences. So quite a set of accolades that she has earned since her time here. I want to make just a little shout out. We're recording this by Zoom to her advisor, Professor Emerita Ghislaine Crozas, because Ghislaine couldn't be here for this, and she would just be delighted, as would Bob Walker, to see Minnie back at Washington University doing this distinguished lecture. But I know that Ghislaine will watch this Zoom recording, and so greetings also to Ghislaine. If all that's not enough, she has an asteroid named after her. And that's pretty spectacular. Asteroid 8356 Wadhwa. Her lecture today is on the exploration of the solar system via sample return missions. So it's a pleasure to have you here, and please join me in welcoming Professor Wadhwa.
Well, thank you so much, Brad, for a very, very kind introduction. This has been such an amazing visit so far. It is kind of like homecoming for me. I was trying to remember the last time I was here, and I think it was close to about 2 decades ago that was the last time, and it's kind of amazing to me that that picture over on the right-hand side actually was taken at that event the last time I was here, 2003, the Walker Symposium. This was right when I think Bob and Ghislaine were getting ready to leave St. Louis to go spend time in Brussels, and this was basically a celebration for Bob, and it was wonderful to be here. And I know I probably came maybe a year later or something like that, but that was the last time. And so, to me, you know, this is as I said, kind of a homecoming. I graduated from WashU nearly 3 decades ago, mind-boggling to me. And really, I mean, as part of the deal, and Ghislaine, as Brad mentioned, was my PhD advisor, but as part of the deal, as value add, I got Bob Walker as an additional mentor, which was wonderful. He used to call me his spiritual daughter, and I still get a little bit emotional about that. But as an international student, you know, that meant so much to me. They were like my spiritual parents, that I sought out their advice for professional and personal things. And they still are. And I know Ghislaine will be watching this, of course. But it's been an honor to come back and to interact with all of the new folks that are here. Well, new, I was just talking to some of the faculty who are really not so new anymore, but certainly feel like new folks to me because I haven't been here in a long time. In any case, so what I'm going to talk about today is a topic that's near and dear to my heart. I'm, of course, a sample scientist, as Brad already mentioned. That's the core of what I do. I started out studying Mars meteorites and meteorites in general. But at the same time, you know, if you're doing planetary sample analysis and you're studying meteorites, the natural thing, of course, is to be interested in materials brought back by spacecraft from other places in our solar system. And of course, I mean, we are exploring our solar system in multiple ways, of course. The remote sensing analyses that many of these spacecraft are doing is incredibly valuable, of course. There's places we are exploring where it's going to be incredibly difficult to actually bring back samples. And that's part of the challenge of sample return missions, is that they are somewhat more complicated in many ways because you have to actually go there. There's not a whole lot, well, there's some science that happens at the target, but most of the science actually happens when you bring back those samples here to Earth, which can mean, of course, the complexity is more, the expense can be more, but the return that you get from that is really pretty unique to these missions and really pretty incredible. And so really, you know, obviously we are exploring our solar system in ways remotely as well as through samples to understand the mineralogy, the chemical composition, isotope compositions of all of these solar system bodies to try to get insights into the processes that were happening within the planetary disk and on planetesimals and on planets, and the myriad of processes that happen on planetary bodies, of course, because we want to understand, of course, how our solar system came about, how did the bodies come about. And now, of course, in the field of exoplanets, of course, we want to understand, you know, how many of these other rocky worlds, how are they evolving, and is there a potential for habitability there as well. So all of these, you know, it's really important, of course, for us to understand these things. But sample return missions provide us with some unique advantages. And I wanted to really kind of quickly touch on those. Number one, of course, the very best laboratories are never going to be on spacecraft. They're always going to be here on Earth. So the best kind of precision that you're going to get, the best spatial resolution you're going to get, it's going to be here in laboratories on Earth. And so that's never going to change, no matter how advanced you get. And so also the ability to do coordinated analyses on the same sample, taking it from one set of analyses and instrumentation all the way through a series of analytical capabilities to really get a coordinated set of analyses and data that then you can put together to really deconvolve some of the complex histories that many of these objects have seen. Of course, in the scientific process, the ability to replicate analyses can be very, very important. And that's something that, of course, if you have samples here, you're able to do that. And in particular, when you think about Mars sample return, that's going to be one where we're going to be looking for evidence of past life. And that's something that you want to be able to definitively replicate in laboratories here. And so that's something that will always be much better off. You'll be much better off bringing the samples here so that you can actually test your hypotheses, repeat the analyses, reproduce your results to really demonstrate that these results are robust. Bringing samples back makes it easier to, of course, analyze them with analytical equipment like synchrotrons that are sometimes the size of city blocks. You're not ever going to put those on spacecraft. I already mentioned that. But you're not limited, of course, by the cost, mass, and schedule constraints of spaceflight in that case. And also, analyses of these well-curated samples is not limited by current capabilities. And this was demonstrated, of course, most recently by NASA's JAXA program, which I know that actually there's people in this room who participated as part of that program. And that was, basically opening up tubes or samples that have been stayed sealed for the last many, decades, and analyzing them with the capabilities that are available and state-of-the-art now to be able to learn new things about the moon and about volatiles on the moon in particular that we weren't able to do when we brought the samples back right in the late 60s when they first came back. And so that's another advantage. And of course, the participation of large numbers of researchers, not just the researchers that are there at the time, but multiple generations of researchers. And there are students now that are, of course, studying lunar samples that were brought back by the Apollo astronauts many decades ago. And so there are training opportunities, there are possibility for a very broad number of investigators to be involved in these. I know that JSC maintains these records of who has requested these samples, and there are literally thousands of samples that have been handed out to, again, tens of thousands of researchers and scientists across the world who have studied and participated in the analyses of those samples. And then, of course, there is the societal benefit, and this is something that, of course, it's not unique to sample return missions, but certainly is true very much so to sample return missions. You have a huge investment in technologies and capabilities that are developed specifically to be able to go to difficult places to do difficult things, and you definitely advance the capabilities here on Earth for the things that you would want to do here as well by putting those investments in. And of course, there's a huge inspirational aspect to these types of activities, and there's many of us, of course, who were inspired by the Apollo missions when they brought back those samples. And for the future, I'm hoping that Mars Sample Return is going to do some of that as well. I know there are actually some in the audience who would prefer to blow up Mars, but I would ask that you refrain from doing so. Anyway, so sample return missions, here's sort of a rogues gallery of all of the sample return missions that have happened so far. On the top left there is captured actually a lot of different missions to the moon, the Apollo missions, of course, in the 60s and 70s. That returned something like over 800 pounds of lunar samples, 382 kilograms, I think. The lunar samples, there were about 300 grams or so that the Soviets brought back. Those were robotic sample return missions in the early 70s. And then most recently, the Chang'e 5 Chinese effort, which actually brought back something like 1.7 kilograms of sample from some of the youngest terrains on the moon. And then, of course, you have a number of these other missions, one to the comet Wild-2, Stardust, which returned with these samples in 2006. The Genesis solar wind mission, which returned with samples of embedded solar wind in these very ultra-clean wafers in 2004, which unfortunately actually crash-landed there. But the important thing is that, you're crashing into Earth, you're coming back to Earth, and so they were actually able to still achieve the top 10 science objectives of that mission because we brought these samples back to Earth, and you could actually recoup those samples, recover those samples, and actually clean up the Utah dirt off of the top. The solar wind was actually embedded below the surface, and so we were still able to sample it and able to actually analyze it. and get a lot of really interesting data. And then the Japanese had a series, well, they have a couple of missions that went to asteroids. Hayabusa was the first one, it returned in 2010, went to Itokawa, an S-type asteroid, and returned a few thousand grains of that sample. And then asteroid Ryugu, and this was Hayabusa 2, which returned in December of 2020 with something like 5 grams. And actually my talk today is going to be focused primarily on that particular mission because I was a science team member of the chemistry team for the Hayabusa 2. And I'll talk a little bit about what we learned from that. But then, of course, just in the last month, you probably saw the most recent return of the OSIRIS-REx sample from Bennu. And that is something that's only just starting, and I know there's people here that are involved in that mission and excited about analyzing some of that sample as well. So before I get into that, I'm just going to sort of very broad brush talk about some of the big picture things that we've learned from at least some of these sample return missions. And again, some of you are probably more familiar with this than others, but it is only from studying these lunar samples that we really got a deeper understanding of how the moon came about. The whole idea of magma oceans on the moon, or magma oceans on rocky bodies, and the idea that in fact many of the rocky bodies in our solar system may have actually underwent this kind of magma ocean phase. It originated from studying these lunar samples, and this is actually a picture of the Apollo 11 regolith sample that John Wood studied, where he was able to find these really bright clouds that are made up of a north side, and just from finding those tiny little grains, he was able to sort of infer that there might have been a lunar magma ocean at some point in the past. And of course, I mean, the studies of these samples have been the impetus for ideas about how the moon formed. The whole giant impact idea, the hypothesis, has come about and has been validated in many ways by the analyses and the data that we have from studying these samples. Another example is the Stardust Will-2 coma particles that were recovered from the tail of comet Will-2 by the Stardust mission. And one of the big discoveries there was a real surprise, was that there were particles in the little grains that were recovered that are very similar to very high temperature minerals and aggregates of minerals that are found in meteorites, called calcium aluminum rich inclusions, which are very refractory grains and objects that are found in primitive chondrites, as well as chondrules, which are also ferromagnesian composition spherules that are thought to be basically described as droplets of fiery rain. So they're basically recording a very, very hot episode in the earliest history of the disk, and they're thought to have formed in the inner parts of the solar system. And here we are finding them as in objects that we think accreted very far out in the far reaches of the solar system, where we actually had expected to find, the solid grains we had expected to find were pre-solar grains, or stardust particles that had not really undergone a lot of processing as part of the disk processes early on in the history of our solar system. But it was a huge surprise to actually find these really high temperature aggregates in these cometary materials. And so what we learned was that in fact the disk processes were extremely important for potentially transport of materials from the inner parts of the disk to the very further reaches of our solar system. And probably there was some kind of, obviously gas turbulence within the disk that may have been one of the processes that was pretty important for this. And so that was, again, a huge surprise, which we, again, learned from these samples that we were able to return. And then, of course, pre-solar grains that have been returned and these pre-solar grains, by the way, this is a field that, Washington University actually was one of the pioneers in the study of these pre-solar grains. And they have been discovered, of course, in primitive meteorites, but have been also now found in these returned samples, validating the fact that, in fact, these materials were ubiquitous in the components of things that actually made up our solar system, the solid objects that actually contributed to the mix of gas and dust, and which were then processed to produce the kinds of materials that we see now as part of asteroidal bodies or rocky planets, etc. And so by studying these three solar grains, and this is, I'm talking here, to an audience where some of the most, I guess, foremost experts in the world have studied these three solar grains, but you can learn a lot. This is basically astrophysics done in the laboratory setting, where you can learn about nucleosynthesis in different stellar settings from looking at the chemical compositions of these types of pre-solar grains. So what I'm going to talk about today specifically in my talk is focusing on some of the results and some of the data that my laboratory was part of acquiring as part of the preliminary analyses from the samples that were returned from the asteroid Ryugu by the JAXA Hayabusa 2 mission. And here's just some of the beautiful images of that object taken by the spacecraft, where you can see the scale bars there, and it's a very rubbly looking object. These things are thought to be sort of like rubble piles in many ways. Their bulk densities are pretty low. But the main point of that mission was to basically understand, the very sort of, what are the building blocks of rocky habitable worlds. And so, we have images like this, the cosmic cliffs from JWST, that show us some of the stellar nurseries where elements are being synthesized right now in stellar environments. And then we have, ALMA images like this one, where we can actually see the gaps in the disk where planets are forming. So you're starting to see the process of, you're really catching planet formation processes in the process by looking at images like that. But how do you get from there to something like this? And that was the big question that Hayabusa 2 was wanting to get at by going to one of the most primitive objects in our solar system, which are thought to be some of these carbonaceous, carbon-rich asteroidal bodies. So the key questions that we have, of course, about our solar system, and this is something that we want to address by looking at a variety of these sort of primitive small bodies, is, how did the solar system form? How did the protoplanetary disk evolve? How and when did the rocky planets form? How and when did the gas giant planets form? What was the raw material that contributed to the formation of these objects? And why is it that the Earth is habitable? What made it habitable? And how did life arise? And from what type of building blocks? And so primitive small bodies, we believe, are actually recording these earliest conditions in the history of our solar system, the protoplanetary disk phase, the initial physical chemical conditions that are part of planet formation. And so, these small bodies, of course, in the current solar system, we know that there are different types of spectral classes of asteroidal bodies in different sort of peak in different parts of the solar system. We know from actually the Hayabusa, the first Hayabusa mission to asteroid Itokawa, which is an S-type asteroid, that this type of asteroid most likely corresponds to a type of chondrite in our collections, which are these ordinary chondrites. They're very obviously rocky, silicate-rich chondritic objects. We think perhaps the E-type asteroids, these might be similar to enstatite chondrites, made up primarily of a mineral called magnesium silicate mineral called enstatite. And then further out as part of the solar system, around about 3 AU or so, you see this kind of peak of C-type asteroids, which we think might correspond to perhaps one of the types of carbonaceous chondrites. And this is sort of a bit of an alphabet soup of different varieties of carbonaceous chondrites that we have as part of our collection, which basically, they're different in the sense of how much water they have, as how much organics and volatiles they contain, and how high of a temperature they've actually seen as part of their evolution. And so some of these, like the CKs, some of them may have seen temperatures as high as 900 degrees Celsius. And then there are others like the C1s that are thought to have actually potentially have had liquid water on the surface of some of these objects because they are accreted with ice. And because of radioisotope decay of isotopes like aluminum-26, which is a short-lived radioisotope which was present in the early history of the solar system but is no longer around because it is so short-lived, that may have been a heat source to melt that ice and produce some amount of water activity, water circulation on these objects. And so you actually see aqueous alteration, fluid alteration, and some of these carbonaceous objects, lots of volatiles. In fact, you can see, for example, here, that in terms of bulk water content, there's quite a lot of difference. And these, even in these carbonaceous objects, from all the way from close to about 10% weight water, down to almost 0 for some of them. And that just tells you that, you know, at least some of them have actually quite a huge complement of organics and water in them. And so, you know, we've obviously had access to chondritic meteorites and meteorites of other kinds. You know, meteorites have been called the poor man's space probes for good reason, because really they provide us with a very cheap way to actually analyze materials that we think came from other places in our solar system. But the downside, of course, is that we don't know exactly where they came from. And so this is an important question that we're trying to resolve as well, is to build that connection between, you know, so these C-type asteroids or these B-type asteroids or these more carbonaceous other classes that we know about, what kind of meteorite do they actually correspond to? And could they have contributed to the complement of volatiles and organics on the early Earth? And so we've learned a lot from studying meteorites, as I mentioned. We know that the age of the solar system, which, by the way, we define, and you can define the starting point of the solar system in a variety of different ways, but this is one of the definitions, is when did the earliest solids start to form within the disk? And the ages of some of these refractory objects, the calcium aluminum rich inclusions that I just mentioned, those actually are thought to represent that time, the formation of the very first solids in our solar system. And this is something that, as Brad mentioned, we dated in my laboratory among other labs who've also done similar work. And we think that that age is 45-68 million years, the time at which the first solid objects started to form in our solar system. That defines T0. We also know from studying meteorites that there were nuclides inherited from previous generations of stars, and some of them immediately prior to solar system formation. So they must have been freshly synthesized as part of either supernovae or other stellar environments, and then injected into our solar system. And I mentioned aluminum-26, that's one of those types of radionuclides, has a half-life of only 700,000 years, and it's fairly abundant. And so we think that that could have been a really powerful heat source for actually melting early planetesimals and planets, and kickstarting that process of differentiation that really kind of has, for example, has resulted in the formation of the layered structure that we see for the Earth, right? The core and mantle and crust. There are, of course, different types of carbonaceous chondrites. I'm sorry, not carbonaceous chondrite, different types of chondrites that are part of our collections, meteorite collections. And they include the carbonaceous, the ordinary, the ancestite. You've heard me mention those types already. And they're not identical in terms of the complement of elements that's present in them. We think the carbonaceous ones are most likely the most primitive, meaning that they are most likely to represent the bulk composition of our sun or the solar system as a whole. But the other types, the O and the E, have some degree of chemical fractionation that resulted from processing, chemical processing within the disk, and most likely high temperature processing within the disk. And so they likely are recording the time and place and the kinds of environments that they were formed in. And as I mentioned before in the previous slide, some of these carbonaceous types of chondrites contain abundant water and organics. And so the idea, the hypothesis that the Hayabusa 2 mission was testing, in a sense, was to say that carbonaceous chondrites are basically representative of the C-type asteroids. And so, but there are different types of carbonaceous chondrites, and they range, as I showed you, in terms of how much volatiles, how much water. And so we really want to find out exactly which type are they most similar to, or are they actually, our C-type asteroids, something that's completely different, not represented at all among the objects that we have as meteorites in our collections. Because there's no guarantee that the things that are falling on Earth as meteorites, they have anything really that's sort of representative of what's out there in the asteroid belt or in our solar system. They might have basically be a very skewed population that we are sampling on Earth. So basically, that is sort of the backdrop of why the Hayabusa 2 mission is then looking at these types of questions about what are C-type asteroids really made of, How did asteroid Ryugu form and evolve in particular? What does Ryugu record about the early solar system history? What's the role of C-type asteroids in delivering volatiles to Earth? So those are the big picture questions. And here's just an image of the spacecraft itself. And here is an image showing the Ryugu C-type asteroid, top-shaped asteroid, which is about 900 meters in diameter. I'm showing on the right-hand side here the trajectory of the spacecraft to get to the orbit of Ryugu, which is a near-Earth asteroid. And so the Hayabusa 2 was actually launched in 2014, and the goal there was to return something between 100 milligrams to 1 gram. And there's a lot that you can actually do with even just a gram of sample. With all of the complement of analytical techniques and capabilities that we have, the Stardust mission, for example, the number of particles that were brought back, they don't weigh any more than maybe a milligram total. So that's, you're talking about extremely, extremely small amounts of samples, but you can learn for something like a gram, you can learn a lot. The spacecraft arrived at Ryugu in June of 2018. It did a first touchdown and sampling event in February of 2019 after it had a chance to do some mapping and get some compositional data for basically surveying the surface of the asteroid and seeing if there was any compositional variability, things like that. It also carried with it, it's called a small carry-on impactor, or SCI, which was a copper projectile. And I think that this is something that NASA probably would never do, but they actually shot at the asteroid, punched a hole in it, and then they actually sampled just a few meters north of that crater to try to get a sample of the internal material from that asteroid. And so these are then the 2 touchdown sites that are shown on the surface of the asteroid. So it sampled 2 places. There are 2 chambers in the capsule that were basically filled with one from touchdown 1, one from touchdown 2. They're called chambers A and C for whatever reason. I'm not sure why they didn't call them A and B, but anyway. This is the actual sampling mechanism. Here's a schematic that shows so it shot a little tungsten bullet into the surface of the asteroid, and it actually sort of released a number of particles that were transported into this little container and put into this little capsule, which is the capsule is the part that returned back to Earth. And so here's a little movie that shows the actual sampling video that happened in 2019. It's a little bit slow to get going, but then you see it literally is a touch and go maneuver. It fires that bullet just as it makes contact with the surface, and you can see a lot of so here it comes. And boop. Almost. And yeah, there you go, all kinds of stuff flying around. Some of it went up that horn and then was captured inside of that little canister. And so you had this little impact event on the asteroid, which captured, so there you go, you see that little small carry-on impactor, the copper projectile that was shot at the asteroid. And then the second sampling event is just about 20 meters or so north of that crater to try to get some sample from inside of or a few meters below the surface. And so eventually those are the 2 samples that were collected. One, as I mentioned, chamber A from touchdown 1, chamber C from touchdown 2. And the total mass of the material recovered was a whopping 5.4 grams. So huge, actually, boatloads of sample, which was awesome. And you can actually see the scale bar here. And these rocks, actually, if you've ever seen a carbonaceous chondrite, this looks very, very much like a carbonaceous chondrite, but we don't know exactly what kind it will be most similar to. So this is actually, I'm just going to show you a couple of slides from a paper that was the discovery paper in some ways. I mean, the initial, actually, the preliminary results were published in this initial paper by Yokoyama et al. 2002, so last year. And here are some SEM images. This is just a backscattered electron image on the left-hand side, and on the right-hand side is a composite chemical map that shows some of the different minerals that make up most of the sample. You can see the scale bar, 100 microns, which is about the width of a human hair. So you're looking at a very small scale here. And you can see minerals like dolomite, which is calcium magnesium carbonate mineral. And this is basically formed as a result of deposition from an aqueous fluid. And that's what I was mentioning, that these objects accreted with ice, which was then melted as a result of some kind of heating process on the asteroid, most likely from the decay of 26 aluminum. And that resulted in the formation of these abundant, relatively abundant, few percent carbonates. And then you've got other minerals. You've got a lot of, the matrix is made up of phyllosilicates, so clay minerals, basically, well, hydrated minerals, actually, that make up the matrix. And you've got other oxides and sulfides, et cetera, as well. And if you were to compare this with carbonaceous chondrites of the C1 variety, CI variety, that's what they look most similar to texturally. Here's the chemical composition. Also, this is from the same paper. And you can see here the concentrations of pretty much the entire periodic table of elements, where you can see all of the elements listed down here on the y-axis, the x-axis. And on the y-axis is the concentration measured in different aliquots of Ryugu by different techniques, and those are all the different colored symbols. And these are normalized to concentrations of these elements in the CI chondrites, so the type of chondrites which have the most abundant volatiles and organics and water, and are thought to be some of the most primitive types of chondrites. And so it's the line at 1 is basically what you would have if everything was absolutely identical to CI chondrites. And in fact, what you see here, and this is a log scale, is that everything within a factor of 2 lies along this kind of flat line. It's not like the CN chondrites, which have this little bit of fractionation that you see for some of these elements that are a little bit more volatile than these other elements that are a little more refractory. And so, first off, you can tell just from the get-go that these objects are actually, Ryugu is actually most similar to the CI type chondrites. That's what it looks like from the whole chemical composition. So we actually got some sample, very, very tiny aliquots to analyze in my laboratory. This was in May of last year. And I just wanted to acknowledge the people that were part of some of the analyses. A couple of my lab personnel, Vinay Rai and Beck Hines, who've been in my lab for a number of years. Nicole Phelan was actually a graduate student who just recently graduated. She was part of some of these analyses as well. And so she helped to perform some of the analyses. The samples that we analyzed, so there were actually 5 different aliquots of the Ryugu samples. Each one between, I think the smallest one was C0002, and that was about 7 milligrams. And then the others were approximately 20 to 25 milligrams. So small aliquots of samples from both the touchdown 1 site, chamber A, or the touchdown 2 site, chamber C. And chamber C is the one that's the subsurface, or had the subsurface component. We also analyzed a number of the carbonaceous chondrites, the CI chondrites, CN chondrites, CV chondrites, and a few ungrouped ones for comparison. And so we actually measured 3 different elements in my laboratory. And we did this as part of sort of coordinated analyses and collaborated analyses with the Japanese scientists. And here's Dr. Yokoyama, who we collaborated on for these analyses, who did independent analyses of independent aliquots so that we could actually verify. And again, this gets back to the robustness of these data. You want to make sure that your data are reproducible, precise, and as accurate as possible. And so we had something like, 1,320 to 200 nanograms of titanium, so very small amounts, nanogram quantities of titanium and chromium, which are, of course, minor elements, trace to minor elements, and then strontium, which is very much a trace element. We are only about 100 nanogram output of that. And so we analyzed those in my laboratory on this. So we have a couple of Neptunes in my lab. And by the way, I just want to mention the names of these mass spectrometers. These are named for a couple of my favorite women scientists that are, I guess, physicists and chemists. Hopefully, I don't know if you can guess who they are, who I'm referring to. Anyone want to take a guess?
Yeah,
Marie Curie. And who's Marge? Margaret Burbage of B square of H. So anyway, so we measured all of them on the Neptune XT, the Marge instrument. And Yoko actually did analyses also of titanium and chromium and strontium independently at other places, University of Tokyo and Tokyo Tech, by Tim's analyses for thermal ionization mass spectrometry for chromium and strontium, and multi-collector ICP-MS, like we did for these elements on our machine. They did titanium that way. So why did we want to measure these particular elements? These are, as I mentioned, minor trace elements. Titanium has 5 isotopes, chromium has 4, strontium has 4 stable isotopes, and that's because some of the isotope signatures for these elements can serve as fingerprints of where they came from, as well as fingerprints of processes that these things have undergone. And so mass-independent variations, particularly of the neutron, most neutron-rich isotopes of titanium and chromium, can be and have been used as genetic tracers, just like oxygen isotopes, the mass-independent variations in delta-17. They can be used as genetic tracers. These variations can also tell us something about nucleosynthetic sources of materials in the protoplanetary disk and the processes that were happening in the protoplanetary disk that homogenize these nucleosynthetic signatures. We also have 2 different chronometers that are embedded as part of these systems. The chromium-53 is produced by the decay of a short-lived radioisotope of manganese called manganese-53. Like aluminum-26, it's also a short-lived radionuclide, and it has a half-life that's only about 3.7 million years. And the manganese-chromium system can be used to obtain relative ages, and I'll tell you why we think those are ages of carbonates, but we can date the carbonate, the aqueous alteration of this material using this chronometer. And then strontium-87 is produced by the decay of the long-lived radioisotope rubidium-87. And this is also, and this has been used extensively, of course, for terrestrial applications as well as cosmic chemical applications to understand nebular parent body processes. So this is basically just to show you sort of that genetic fingerprinting aspect of chromium and titanium isotopes. So this is actually from a paper by Warren, 2011, where if you plot the titanium-50 excesses versus the chromium-54 excesses, and here are what's actually being reported here. This is a 50 to 47 titanium ratio relative to a terrestrial standard in parts per 10,000, and the 54 is basically the 54-52 ratio in the same kind of notation. And so what we find is that carbonaceous chondrites define an area of this plot that's way up here on the upper right, and each one of the types, the C1s are here, CMs are up here, COs are up here, CKs up here. And so they're in different parts of this little field, but they're very distinct from things that we think formed in the inner parts of our solar system. So the Earth, the Moon, and Mars. Basically, Mars is from Mars meteorites, by the way. We don't have samples of Mars yet to analyze in the laboratory. Ordinary chondrites fall in this region here as well. Some of the other types of meteorites fall in this area. We think that these non-carbonaceous meteorites, they fall in this region because they formed in a very different part of our protoplanetary disk than where these carbonaceous chondrites formed in. And these carbonaceous chondrites actually, we think, formed further out in the outer reaches of our solar system. And the way that this actually happened, the reason why they have these very distinct compositions in terms of these trace signatures is because these 2 parts of the protoplanetary disk were separated from each other early on in the history of our solar system by the formation of Jupiter early on, which basically separated these 2 reservoirs completely. And what had to happen to create these distinct compositions was that the material that was falling or accreting into the disk had to evolve over that time period. From material that was originally quite enriched in nuclides that are formed in neutron-rich stellar environments, so things like titanium-50 and chromium-54 had to be enriched early on. And then the composition of the stuff that was falling into the disk evolved or changed over time to less enriched in these types of isotopes. And in the meantime, you had Jupiter forming, which then, of course, kept these, made these reservoirs very separated from each other. And you no longer was able to have sort of transport of materials from here outwards or mixing across that disk. And so that's what we think was going on physically that actually created those distinct reservoirs. And so that the end product is that you do have these two distinct reservoirs in terms of these isotope systematics. The Yokoyama paper that looked at the initial compositions of the two touchdown sites basically found that the composition of Ryugu was very similar, actually fell in generally in the area of CI chondrite. It didn't look very different. The two sites didn't look very different. So we went back and analyzed those multiple fractions that we got. And basically, this is what it looks like. You notice, of course, the error bars are much smaller in this case of the new analyses. And they're actually resolvable differences between different aliquots. But it's not what you expect in terms of maybe one touchdown site being completely different from the other. You're actually seeing variation between, even at the same touchdown site, for example, here, you're seeing this sample basically resolvably distinct from this sample, even though they come from the same touchdown site. And same thing you see replicated here. And that's kind of intriguing. I mean, there's definite variation in these. And you're seeing actually that it's varying in the chromium isotopes. It's not varying in the titanium isotopes. The titanium isotopes basically within errors are the same. And so this is telling us something about some kind of processes that are happening on the parent asteroid that we can learn something about. If you, however, take the bulk mean of all of the samples taken together, it actually falls squarely within CI chondrites. There's a slight overlap here with CBs, but CBs are a completely different beast. These are metal-rich objects, which are actually, that basically Ryugu looks nothing like that. So we're not even going to talk about that because it's not anything like it. The clue about why you're seeing this variation comes from looking at the signature of chromium-54 relative to chromium-53. Now, chromium-53 is the radiogenic daughter of manganese-53. It's being produced by a completely different process than the chromium-54. And what you see here among the samples, Ryugu samples, is that there's this downward trend going from high chromium-54, low chromium-53 in some samples, to low chromium-54 to high chromium-53 in some samples. And we think that this has to do with the fact that you're mixing sort of the indigenous material that was essentially dominated potentially by a nucleosynthetic component, mixing that with a secondary phase that is basically most likely, we think, the dolomites or the carbonates, which have, we think, very obviously they were formed at a later time and basically did not have very much of the chromium-54, the nucleosynthetic anomaly. But because they have very high manganese-chromium ratios and they formed early on, there was likely to be live 53 manganese, and which had, of course, decayed, of course, to the 53 chromium. And so you actually had this end member be the dolomites. And so we think that the reason why some of these fractions are so different from each other, this has to do with redistribution of, or heterogeneous distribution of two very separate components, one that's pre-solar and one that is the secondary alteration component in these objects. And so that can only really happen as a result of water circulation on that asteroidal parent body. And we think that's what's causing the difference between these. The other thing that we can do with the system, of course, is get a relative age of formation of the carbonates, because manganese chromium is fractionated it's actually not by any other kind of process except basically carbonates have extremely high manganese contents and very low chromium. And so when they are formed, they actually tend to fractionate this particular element ratio quite significantly. And so this is an isochron plot, manganese chromium isochron plot, and the slope of the line actually gives you the initial abundance of 53 manganese that was present at the time, live at the time of the formation of these carbonates. And we think it's the carbonates, by the way, that are actually causing this linear spread along this line, because you can actually, we did this mass balance calculation, which shows that if you start out with something that's a bulk CI chondrite and you mix in different amounts of the dolomite of the composition that we find in the Ryugu materials, they all line up along this line, which basically is either a subtraction of that dolomite component from bulk CIs or an addition of a dolomite component. And so that's what's causing this spread that you see in the manganese chromium ratios. And this is basically then giving you a relative time of formation of these carbonates of something like 5 million years after the start of the solar system. And again, the start of the solar system being the time at which the first solids were starting to form. And so we can do that kind of relative dating with this method. And so that's the very first sort of takeaway then from this, is that Ryugu is most similar to CI chondrites. That's number one. We confirm that with the titanium chromium. And we think that the variation that we're seeing in chromium isotopes, but not in the titanium, and titanium is not very mobile, so it's not being affected by this kind of labile behavior that we're seeing for chromium. It's most likely to do water circulation on the Ryugu parent body. So that's an important takeaway. And then the formation of these secondary carbonates, the timing of that, it happened within 5 million years of the formation of our solar system. I'm very quickly going to go into the rubidium strontium. I'm not going to spend too much time, but what you see here are the data for Ryugu, and they line up very well along the reference isochron. This is the 4.56 billion year reference isochron. This is, by the way, these samples are not defining strictly an isochron at all. This is just scatter plot, really. But to first order, what they are telling us, they're telling us a couple of things. Number one, that you see that there's a spread in rubidium strontium ratios among these samples. And we think that probably that has to do with the carbonates, again, with the secondary carbonates. We know that those secondary carbonates formed within 5 million years. The precision of the rubidium strontium system, because it's such a long-lived system, is actually tens of millions of years. So within that time frame, you spread, because of carbonate formation, you actually spread these data points along the 4.56 giga-year isochron, roughly speaking. What you do see is that the sample, again, look at this C108 sample here. This is the one that's least affected by the addition of dolomite. And that's the one that's closest to the range of CI chondrites that are these black diamonds that are shown here. And so the secondary carbonates, the addition of greater abundance of secondary carbonates draws these sort of bulk samples down towards these other compositions where Murchison and other CM-type chondrites are. So that's a secondary process. The original material was most similar to CI chondrites. And so that's basically then the takeaway from the strontium analyses, is that Ryugu materials date back to the beginning of our solar system, 4.56 billion years ago. Variation, most likely, again, this is confirming what we already found from chromium isotopes, that this is because of extensive aqueous alteration. They all fall within, again, the CI carbonaceous chondrites. That's the least affected by carbonate addition, and that's the composition most similar to CI chondrites. And so in summary then, we have this history of Ryugu, that basically this C-type asteroid is most similar to CI carbonaceous chondrites in our collections. Most of these components that formed Ryugu were formed 4.56 billion years ago. The secondary carbonates were as a result of water circulation on that asteroid about 5 million years after the formation of the solar system. And then the alteration processes, the circulation of liquid water, actually redistributed some of the original components in a way that caused them to be heterogeneous on the sampling scale that we are analyzing. So that's sort of the big takeaways from that. I just wanted to say, of course, that we have the OREX samples. We have another set of carbonaceous materials here. We're just starting, maybe, I don't know if Kumai is ready to tell us at all whether this is similar to CI or CM or whatever this is, but I can't wait to find out. We're hoping to be able to analyze some of these materials in my laboratory once they become available relatively soon. looking at it from some of the initial first look of these materials, it certainly looks carbonaceous, but again, it'll be difficult to really know exactly what this is until we analyze them. What I did want to end on was just this little teaser for tomorrow. I'm going to talk about the Mars sample return and my involvement in Mars sample return tomorrow, but I'm definitely looking forward to and very excited about what we're going to learn from these samples. The big, of course, science goals for that, we want to understand the geologic context for Mars. We want to understand the climate evolution. We want to understand the potential for life on Mars, which will tell us something about where and how life originated on the Earth as well, potentially. And so I want to end here with a little video of Mars sample return. Come to my talk tomorrow if you want to learn more about that. But this is basically the sample retrieval ladder getting to Mars at night. As Perseverance, by the way, is collecting samples right now. Likely not going to be collecting the last sample right as the ladder gets there. Now the ladder for Perseverance is planned to be the primary delivery pathway for the samples to the ladder. Here you see the transfer on grabbing these tubes that are about the size of a chalk and putting them in this canister called the orbiting sample canister. Then you close it up, load it up, the nose of the chalk, and it's the first time that we're launch a rocket on the space of the planet. That's air launch. This is very awesome. We do it all the time here on Earth. And we're going to launch that little canister in the bottom. And this is then going to be captured by another spacecraft called the Return Orbiter. Captured by a spacecraft. And the canister transferred into a
We have time for some questions.
Awesome talk. Quick question on the fluid activity. So you mentioned that there was some fluid activity about 5 million years after the first solids. The fact that you can observe that and infer that, does that tell you anything about the migration history of the asteroid? The fact that there's fluid activity.
So we think that the fluid activity happened as a result of heating of that asteroidal parent body from the decay of short-lived radioactivities like aluminum-26. And so I don't think that that is necessarily related to the migration. And I think that there certainly was an evolution of where these asteroidal parent bodies may have been from where they were originally formed to where they are now. But I don't think that that particular date has a bearing on that particular question. So all that's telling you is that the parent asteroid was heated up, and we think that most likely, this is within the lifetime of 26 aluminum, and that's been implicated in the heating of other small bodies in our solar system as well. We see evidence of it. And so, yeah.
So I have a sort of a related question, and that would be, did the water start out as ice? And
Yes.
so was this, they form sort of far out in the solar system beyond
Yes.
the ice line?
Exactly. So that's I think I mentioned that very briefly, but I kind of went back quickly. But yes, so there is a snow line, that's an evolving, it's not an absolute where it is. Of course, it depends on how the disk is evolving, but there is ice being condensed in the farther reaches of our solar system, which is where we think many of these carbonaceous asteroids, the ones that are volatile rich, accreted beyond that snow line, and so accreted with ice as part of the mix. And so when but there was also a rocky complement as part of, part of that material that accreted, and that rocky complement contained some 26 aluminum as part of that, and so that resulted in the heating up of the accreted material within about 5 million years. And just by the way, the 5 million year time scale, there are manganese chromium dates of carbonates and carbonaceous chondrites, and that's about, it's a few million years after the start of the solar system as well. So there's evidence in carbonaceous chondrites that there was carbonates forming as a result of aqueous activity on the parent bodies of those meteorite parent bodies. But now we're seeing this in these return samples, additional evidence of that.
Many excellent talk, good hour. I do have a comment. Many of us here work very hard to make sure the data being collected by these spacecraft missions, in fact, are made available and useful for coming generations. So it's not only sample return, that provides interest in terms of STEM and increases, discoveries, but having data from the various missions is both complementary to the sample return.
Yes.
And also, there'll be discoveries over the next decades, that the original team members never really realized.
Yes, no, absolutely, and I totally do not intend to give any kind of short shrift to other missions like
to it.
kind of stuff. Yes, I mean, it's a treasure trove of data, and I think that's what, NASA really needs to provide more RNA opportunities to study all of the, wealth of data that's already there from many of these missions. I know that some of the, even the MER data and the Curiosity data, much of it, people have not really kind of, exploited it as best they can, actually. So I think there's lots to learn from some of
As
that.
you know, Ray, Tom Stein and others in this room are very much interested in making sure we have all the information about these marvelous Mars samples.
Yes, absolutely.
And that we'll have it 10 years from now when we get samples back.
Yeah.
Quinn, you want to tell us about? Yeah.
Do you have anything to say about water on Earth?
Yes, so, the fact that we actually see these asteroidal bodies that are very volatile rich and have a huge complement of water. So we think, the abundance of water is 8 to 10%, weight percent. That is plenty. Oceans more than what, if we had, depending on how many of these types of objects would have impacted Earth, but these could easily have delivered the complement of water that we find on the Earth. So, yes, I think that's a very active area of study, actually. People are, and this is something that my group is involved in also, to look at, hydrogen isotope compositions of materials like the Ryugu samples, that I know that people are studying that, as well as chondrites and other types of objects, and comparing them with the DOH of reservoirs on the Earth to sort of make that connection. And we think, yes, that these types of objects did contribute the water for the Earth.
Other questions?
Hi, Minnie. That was a great talk. I was excited. You had shown the sort of older titanium and chromium isotope plot, and I remember seeing that and thinking, okay, there's this non-carbonaceous trend kind of pointing at the middle of the carbonaceous trend.
Yeah.
And then in your updated, more recent figure, it sort of looks like the non-carbonaceous is pointing at the CI end. Was that the same plot?
Yes, so let me see if I can pull this.
My question was sort of, do you think it might be 3 components?
Oh, I see. So this is, it's different ways of showing it. One shows sort of an average with a standard deviation to show the range, and these are, and then there are these sort of ellipses that are showing sort of full range of compositions, right? And so, again, I think there's been a number of different thoughts about, what's causing these sort of trends and why it is that you're seeing the spread in compositions that you are. There's actually some work actually done on Ryugu samples. I think ionized compositions of some of these Ryugu samples that's even pointing to like a third reservoir that's completely distinct as well. But yeah, I mean, it's only speculation at this point that I could make about that, and whether it's, I don't, I mean, I don't know if there's any particular sort of, it's not pointing necessarily to the CIN, I would say, but it's towards that N. And I don't think that really changes when you look at it from this perspective.
Right.
And so I don't know whether this, the range of compositions that you're seeing in the NC meteorites means that there's something that's at the CIN or close to that that's actually mixing in. But I mean, this broadly speaking, what this is explaining in the context of the, addition of infalling material that's sort of distinct and different compositions. And there's of course going to be some amount of mixing between these two reservoirs, so maybe it's not unexpected, but yeah, I mean, probably some kind of carbonaceous composition down at this range.
Thanks.
A little bit on wavy, I know, but.
Getting your exercise. Sorry for making you work. It's good.
Hi, Minnie. I loved your talk. On the basis of these samples, can we say anything about the size or properties of that parent asteroid and what kind of processes might have been going on there for there to be hydrothermal alteration of these things?
Yeah, so on the basis of just these analyses, I think, obviously this particular body itself, the 900-meter rubble pile assembly, that it's nowhere near close to the original size of the object, we don't think. I mean, so we, could have been a larger body, but obviously, it's a primitive. The compositions that we're seeing recorded are primitive enough that it couldn't have been a massive body, so it didn't obviously melt as a result of decay of 26 aluminum. So it accreted early, and so it had to be sort of during a time when 26 aluminum was live, but it couldn't have been so massive that it melted. So I mean, I think, again, I don't know that there's been any quantitative constraints that have been made so far, at least. But it looks like it probably was not such a massive body that it, the current object, of course, has a lot of gaps and holes and porosity, and so I don't think it says anything about what the original size of the object was. So yeah, I don't know, smallish body, I would say.
Well, Minnie, one of the things you've shown us is that the more elements we can analyze and the more isotopes we can analyze, the more complex our understanding of these processes becomes.
More in-depth, I would say.
And more questions that we can ask. Speaking of which, other questions? Well, let me ask just one question about Mars. I can't wait till tomorrow night to ask this question. There are a lot of scientific reasons to have samples of Mars back, but are there reasons that we must have samples back before we can send humans to Mars?
I think so. I mean, just, it would behoove us to actually show that we can actually bring rocks back before we start to think about bringing humans back, don't you think?
No, I was thinking of things like the planetary protection that NASA has for many years, said we must have samples before we send humans.
Yes, no, I think that there may be reasons for not sort of being so explicit about it as requiring it necessarily, because I know that the human exploration side of NASA maybe does not want potentially to get involved in paying for Mars sample return in some ways, and so I mean I think they don't want to make it so dependent that it becomes sort of part of the goal of prior to human exploration you're going to have to do it. But I absolutely feel very strongly that yes, we will learn a lot about, especially from the regolith samples that have been collected, the composition of the globally average dust that's going to be all over the spacecraft and all over the astronaut suits and things like that, which are then there's, thought to be perchlorates and other things in as part of the mix of the regolith, and astronauts are likely going to be, bathed in this stuff and could be breathing this stuff. And so I think it will be important for us to understand what the composition of these materials are. What are the trace phases that are in there that could potentially have some relevance in terms of hazard? So yes, I think that they'll be hugely important for designing systems and planning for human exploration of Mars. So yeah, I certainly stand by that.
One last chance at questions? Oh, sorry.
So I guess on the surface of the asteroid, everything gets kind of like the UV light destroys every living material. So if you dig a little bit deeper, do you get organic or biological material?
No, so I think that the return categorization of these objects from small bodies is not restricted return. Just like for Mars, it is restricted Earth return because of the potential for, though that potential is actually very, very low. Mars itself, the surface of Mars has been bathed in, highly exposed to radiation as well. And particularly the region that we're collecting these samples in, it's not one of the special regions of Mars that we think might still have some, liquid water on there and things like that. So that's even a low potential. But these small bodies, I think that they've been exposed to radiation and in environments where we don't think that there's any potential for really extant biology there. There could certainly be prebiotic organic compounds, and we know that there are. Actually, there's been analyses of the Ryugu material that has shown a detection of uracil compound, which is one of the sort of components of nucleobases. And so these prebiotic components, they certainly are present, but there's really no real, there's not been demonstrated to be any potential for biology.
Okay, if there are no other questions, let's thank Professor Wadhwa again for